Okay, hi everyone. In the last class we discussed vibrational spectra of diatomic molecule by taking simple harmonic motion. We discussed vibrational spectra of diatomic molecules by taking simple harmonic motion. Now we have to see vibrational spectra by taking enharmonic motion. Now, enharmonic motion. If you take real bonds, whether real bonds follow harmonic motion or enharmonic motion, you see, real bonds do not follow simple harmonic motion. They may follow simple harmonic motion up to small extent only. Okay, according to simple harmonic motion, okay, the bond may undergo stretching by any extent. There is no any limit. The bond can undergo extension by any limit. Okay, so without breaking up the bond. According to simple harmonic motion, the bond undergo extension to any distance without breaking up the bond. But real bonds are not elastic to that extent. Real bonds are not elastic to that extent. Real bonds may participate in the breaking. Okay, where generally whenever bond length increases by greater than 10%, generally if bond length increases by greater than 10%, then bond may gets breaking. So this breaking of bonds is not considered in simple harmonic motion. That means real bonds follow simple harmonic motion only up to certain extent only, up to certain extent of vibration. Okay. So real bonds follows which motion actually? Enharmonic motion. Okay, so real bonds follow Hooke's law up to certain extent only. Okay, for greater extent of vibration, they may not follow Hooke's law. They may undergo breaking. So that is called enharmonic motion. So by taking simple harmonic motion, the expression for potential energy we discussed 1 by 2 kx square. So which gives parabolic type of graph. Okay. By taking into consideration of enharmonic motion, Morse proposed an empirical equation for potential energy. The equation is dE into 1 minus exponential of A into Re minus R whole square. Okay, this is the equation proposed. Okay. This is whole square. This is the equation proposed by Morse for potential energy by taking into consideration of what? Enharmonic motion, by taking into consideration of breaking of bonds. Okay, here A is a constant. D is called as dissociation energy of the molecule, or that is nothing but well depth. Dissociation energy or well depth. Re is equilibrium distance, bond length. Equilibrium distance. R is the distance between the particles. R is the distance between the particles. Re is equilibrium distance between the two atoms, diatomic molecule if you consider. So according to this equation, if you plot a graph between potential energy and internuclear distance, the distance between the two atoms. So according to simple harmonic motion, we will get a graph like this. According to simple harmonic motion, we will get a graph like this. Now by taking into consideration of enharmonic motion, we will get a graph like this one. So at a certain extent, the bond gets broken. At a certain extent of extension, internuclear distance, the bond gets broken. This is called what? Equilibrium distance. This is equilibrium distance. This is well depthened. Okay. This well depth is said to be dissociation energy. This well depth is said to be what? Dissociation energy, DEN. Dissociation energy, DE. So this is the expression proposed by Morse for potential energy by taking into consideration of enharmonic motion. Okay, now what are the various possible vibrational energy levels? What are the selection rules? And where we are getting the signals? That is important. Okay. So what is the expression for energy and vibrational energy levels? That is obtained by solving Schrodinger wave equation. So directly I am giving the equation V plus 1 by 2 into omega bar E minus V plus 1 by 2 whole square omega bar E Xe. V plus 1 by 2 into omega bar E minus V plus 1 by 2 whole square omega bar E Xe. V is called vibrational quantum number, same. The possible values for V are 0, 1, 2, 3 and so on. Xe is called enharmonicity constant, that is constant whose value close to 0.01. Xe enharmonicity constant, its value close to 0.01, and omega bar E is called as oscillation frequency or vibrational frequency, that is called as oscillation frequency or vibrational frequency. Okay. So the possible values for V are 0, 1, 2, 3 and so on. Okay. Those who are preparing for GENCO, the derivation is not required. You may concentrate on final conclusions. So E0, if you substitute here, we will get 1 by 2 omega bar E minus 1 by 4 omega bar E Xe. E1, if you substitute E1 here, we will get 3 by 2 omega bar E minus 9 by 4 omega bar E Xe. E2, if you substitute here T, 2 into 2, 4, it is 5 by 2 omega bar E minus 25 by 4 omega bar E Xe. Like this, we will get various possible vibrational energy levels. And if you see the gap between two successive vibrational energy levels, so previously what is the equation we have? V plus 1 by 2 into H nu or nu bar we have, V plus 1 by 2 into H nu or nu bar we have. Here we are getting one extra term and V plus 1 by 2 whole square omega bar E Xe by taking enharmonic nature. Okay, gap if you see 3 minus 1 to 2 by 2 gets cancelled, omega bar E minus 9 plus 1 minus 8 by 4 2 omega bar E Xe. Okay, here if you see 5 minus 3 2 by 2, that is 1 omega bar E minus 25 plus 9 minus 16 by 4, that is minus 4 omega bar E Xe. Like this we are getting successive gap between successive energy levels. Here omega bar E same, omega bar Xe, omega bar Xe both same, but here 2 times we have to subtract, here 4 times we have to subtract. That means as V increases, what about energy gap? Decreases. If you take simple harmonic motion, energy gap is same, so equispaced energy levels we got, but here as vibrational quantum number increases, okay, energy gap decreases. That means before dissociation almost we will get continuous energy levels. This is the dissociation energy. This is the dissociation energy. Whether 0 point energy is 0 or not equal to 0. 0 point energy is not equal to 0. This is E0. Next E1. What about gap? Decreases. This is E1. For example, E2, E3, okay, E4, and at dissociation, near dissociation, almost we will get continuous energy levels. The energy gap may vanishes as V increases, delta E decreases, and near dissociation, what happens to energy gap becomes 0. We may get continuous energy levels. So this is this well depth is called what? Dissociation energy dE. Dissociation energy dE. But experimentally, if you calculate, experimentally obtained dissociation energy is this one only, D naught I am indicating. Actual dissociation energy or true dissociation energy is D naught only, since ground state energy is not equal to 0. Whether ground state energy is 0 point energy is 0 or not equal to 0, not equal to 0. So according to Morse, D is the dissociation energy, but true dissociation energy is not equal to DE. True dissociation energy is equal to D naught. That's why DE may be considered as well depthened. That is well depthened. So DE is nothing but what? D naught plus 0 point energy. So actual ground state energy is nothing but well depth minus, okay, with respect to potential energy minimum we have to take, and with respect to well depth we have to take. D naught means with respect to 0 point energy. So D naught is equal to DE minus E naught. E naught is nothing but ground state energy. Okay, so out of these 3 parameters, 2 parameters may be given to you. They may ask you third parameter. Well depth is DE, okay, with respect to minimum in the potential energy curve, but with respect to ground state energy or 0 point energy, that is D naught. D naught is considered as what? Actual energy or true energy, true dissociation energy or experimentally obtained dissociation energy, since E naught is not equal to 0. Okay, so these are the various energy levels we are getting at. Okay. As vibrational quantum number increases, energy gap decreases. Next, if you see selection rules, what are selection rules? According to harmonic nature, plus or minus 1 only. But for enharmonic nature, plus or minus 1, plus or minus 2, plus or minus 3, and so on. Another condition is the dipole moment of the molecule has to be changed during vibration. The dipole moment of the molecule has to be changed during vibration. Okay. Now, for example, if you take delta V is equal to plus 1, that is V is equal to 0 to V is equal to 1, such vibration is called fundamental vibration or fundamental transition. Generally, the population in the V is equal to 0 state is more compared to higher vibrational energy levels generally. So that's why the intensity of spectral line corresponds to fundamental transition is higher. Generally, intensity of spectral line corresponds to fundamental transition is high compared to other transitions. Why its intensity is high? Generally, the population in the ground state is high compared to higher vibrational energy levels. Now, where we get signal corresponds to fundamental transition. So, how much energy is absorbed during this transition? Energy absorbed is nothing but the gap between those two levels. So, EV is equal to 1 minus EV is equal to 0. Already we calculated, we got what? Omega bar E 1 minus 2 XCN. As XC value is very, very small, 0.01, almost this is negligible. So, almost we will get at omega bar En. So, the signal corresponds to fundamental transition is observed at omega bar En. Okay. If XC value is given, you may follow this equation. Next one, delta V is equal to plus 2 is also possible according to selection rules. Delta V is equal to plus 2. Such transitions are called overtones. Such transitions are called overtones. Here, directly 0 to 2 I am taking. V is equal to 0 to 2. This is called as first overtone. That is called as first overtone. If directly the transition takes place from 0 to 3, that is called as second overtone. Generally, the probability for this type of transitions are low, so generally their intensities are low. Generally, the intensities of overtones are low compared to fundamental transitions. Okay, so 0 to 2, if you see what is the gap, we will get it once you may calculate. We will get 2 omega bar E into 1 minus 3 XCN. 2 omega bar E into 1 minus 3 XC. If you calculate the gap between second level and 0th level, 2 omega bar E into 1 minus 3 XCN. Okay. Next one, delta V is equal to, if you take plus 3, V is equal to 0 to 3. V is equal to 0 to 3. That is called second overtone. Still, its intensity is very low. Okay. If you calculate where we will get the signal and where we will get the signal corresponds to second overtone. That is observed at the gap between third level and the 0 level. You may calculate that gap. We will get 3 omega bar E into 1 minus 4 XCN. Okay. XC value is small, so that means almost we will get at 2 omega bar E. This we will get almost at 3 omega bar En. So, we will get 3 signals corresponds to fundamental transition, first overtone and second overtone at nearly omega bar E, 2 omega bar E and 3 omega bar En. And last one, hot bands. Hot bands. The transitions occurs from higher energy levels. Okay, in the previous case, all the transitions we considered from 0 level, ground state, 0 to 1, 0 to 2, 0 to 3. If you consider the transitions from higher energy levels, higher vibration energy levels, the corresponding signals are called hot bands. And the corresponding signals are called hot bands. These are called as hot bands since generally these are observed at high temperatures. Generally, these are observed at high temperatures. Since these transitions occur from higher vibration energy levels, at lower temperatures, higher vibration energy levels may not populated, only ground vibration energy level may be populated. So if you increase the temperature, as the temperature increases, what happens to higher vibrational energy levels? Higher vibration energy levels also populated, and the population in the higher vibration energy level increases. In such cases, we observe hot bands. Okay, I am taking the first hot band, that is V is equal to 1 to V is equal to 2. Previously we considered 0 to 1, like that we considered. V is equal to 1 to V is equal to, what is the energy gap we got? V is equal to 1 to V is equal to 2. Energy gap we got V is equal to 1, we got what? 3 by 2 omega bar E minus 9 by 4 omega bar E XE. 2 means we got 5 by 2 omega bar E minus 25 by 4 omega bar E XE. This is E2 and this is E1, this is E2. Okay, V plus 1 by 2 we have. So E2 minus E1, what we got? 5 minus 3, 3 by 2 by 2, that is omega bar E minus 4 omega bar E XEN. So omega bar E, if you take common, 1 minus 4 XE. 4 XE value small, almost this is also observed at omega bar E end. First hot band is also observed at almost at omega bar E. Okay. Why these are called hot bands? And these transitions occurs from higher vibrational energy levels. Higher vibrational energy levels are generally not populated. If you increase the temperature, those levels are also populated. In such cases also, we may observe these hot bands. Okay, these bands we observe, that's why these are called hot bands. This is one example. First hot band, that is V is equal to 1 to V is equal to 2, that is observed at omega bar E into 1 minus 4 XE. Okay, how we can confirm whether hot bands are present or not in our spectrum? Okay, we have to increase the temperature. Okay, we have to observe the same spectrum at different temperatures. Okay, whenever we are increasing the temperature, if the intensity of signal is increasing, if intensity of signal is increasing, that indicates that it corresponds to hot band. Whenever we are increasing the temperature, if the intensity of a signal increases, that corresponds to hot band. Okay, this is about enharmonic nature. So from enharmonic nature, you may remember Morse expression for potential energy, dE into 1 minus exponential of A into Re minus R whole square, where dE is called dissociation energy or well depth. This you may remember. The expression for energy, vibrational energies. As vibrational quantum number increases, what about energy gap? Decreases. Okay. Next, the relation between actual dissociation energy and the dissociation energy according to Morse curve. That is D naught plus E naught. This is what? True dissociation energy. Fundamental bonds. After that, selection rules you have to remember. Plus or minus 1, plus or minus 2, plus or minus 3, and so on. These are selection rules. You may remember that. Fundamental bands, where we have observed fundamental bands, omega bar E 1 minus 2 XE. First overtone 2 omega bar E 1 minus 3 XE. Second overtone 3 omega bar E 1 minus 4 XE. And hot band omega bar E 1 minus 4 XE. This 4, where we are getting these 4 signals, you may remember. And since they are giving energy gap, they are asking omega bar E XE, like that they are giving questions. And okay, so these are the points you may remember from enharmonic nature. Next I am giving rotational vibrational spectrum. Rotational vibrational spectrum. So diatomic vibrating rotator. I am taking what? Diatomic vibrating rotator. Previously we considered rotational spectrum separately, vibrational spectrum separately. Now, okay, pure rotational spectroscopy is not possible actually. Whenever molecule goes from one vibrational energy level to another vibrational energy level, in between vibrational energy levels, whenever molecule goes from one vibrational energy level to another vibrational energy level, in between vibrational energy levels, what we have? Rotational energy levels. So that means rotational transition also occurs simultaneously. So it is not possible to get pure vibrational spectroscopy, and it is not possible to get pure vibrational spectroscopy. Whenever vibrational transitions occurs, rotational transitions also occur. Since in between vibrational energy levels, what we have? Rotational energy levels. Okay, so in practice we cannot get pure vibrational spectrum. So now we have to consider both rotational motions and vibrational motions. Okay, and we are considering here rotational motions and vibrational motions are independent. And here we are taking an assumption according to Born-Oppenheimer approximation. According to Born-Oppenheimer approximation, let us consider vibration motions and rotational motions are independent. Okay, independent means no coupling between rotational motions and vibrational motions, no interactions between rotational and vibrational motions, both occur independently. Okay, then total energy is given as sum of the rotational energy and vibrational energy, and then total energy of the molecule is given as sum of the rotational energy and vibrational energy. To consider rotational energy, what we have, Bj into J plus 1. To consider vibrational energy, enharmonic nature, real bonds follow enharmonic motions. So V plus 1 by 2 into omega bar E plus V plus 1 by 2 into whole square minus V plus 1 by 2 into whole square omega bar E xc. This is the energy expression by taking rotational motion and vibrational motion. Okay. So now in this equation, if you substitute J value 0, 1, 2, 3 and so on, V value 0, 1, 2, 3, we'll get various rotational and vibrational energy levels. What about selection rules? Selection rules, if you see, for rotational spectroscopy, what we have, delta J is equal to plus or minus 1. Rigid diatomic vibrating rotator we are taking. Okay, diatomic vibrating rotator we are taking, delta J is equal to plus or minus 1. Okay, here we are assuming rigid diatomic molecule, and even though molecule undergoing vibrational motion, we are assuming that no change in the bond length. Since during the vibration, the change in the bond length may be negligible, so that we are neglecting it. We are taking rigid motion, and for rigid motion, what is the selection? We have delta J is equal to plus or minus 1. And for enharmonic motion, what about the selection? We have plus or minus 1, plus or minus 2, plus or minus 3, and so on. So these are the selection rules. In this, if we consider delta J is equal to plus or minus 1 and delta V is equal to plus 1, and only we are taking one specific case, delta J is equal to plus or minus 1, delta V is equal to plus 1, since most of the transitions occurs from 0 level to first level, and that transition we are taking. Okay, higher vibrational energy levels are not populated, lower vibrational energy levels are highly populated, so this transition we are taking. So for this, if you calculate energy gaps, and for this if you calculate energy gaps, final equation we will get like this, omega bar naught plus 2bm, where omega bar naught is omega bar E into 1 minus 2xm, where omega bar naught is omega bar E into 1 minus 2x. That is nothing but fundamental transition. The gap corresponding to fundamental transition, 0 to 1 is means fundamental transition. How much gap we got? Omega bar E minus omega bar E into 1 minus 2x we got for fundamental transition. So here 0 to 1 means what? Fundamental transition. So that is omega bar naught plus 2bm. What is m? M possible values for m are plus, m is j plus 1, and the possible values are plus or minus 1, plus or minus 2, and so on. M values will get positive if delta J is equal to plus 1, and M value will get negative if delta J is minus 1. Okay, if you see clear derivation, I am not giving that derivation part. This is the final equation we will get. Delta E is equal to omega bar naught plus 2bm, where omega bar naught is omega bar E into 1 minus 2xc. The possible values for m are plus or minus 1, plus or minus 2, and so on. Positive values we will get if delta J is plus 1, negative values we will get delta J is equal to minus 1. So if you take delta J is equal to plus 1, where we will get the signals, and various signals are observed at omega bar naught, m value plus 1 if you substitute. Delta J is equal to positive, delta J is equal to plus 1, m values are positive, and plus 1 if you substitute, what will get? Omega bar naught plus 2b. Plus 2 if you substitute, omega bar naught 4b. Plus 3 if you substitute, omega bar naught plus 6b, and so on. Similarly, if you substitute delta J is equal to minus 1, various signals we will get at omega bar naught minus 2b, omega bar naught minus 4b, omega bar naught minus 6b, and so on. So like this we will get various signals and corresponding to delta J plus 1 transition and delta J minus 1 transition. Plus 1 transition means, for example, 0 to 1 and 0 to 1. Minus 1 transition means, for example, 1 to 0, 1 to 0. In the lower vibrational energy level, okay, rotational quantum number is 1. In the lower vibrational energy level, rotational quantum number is 1. In the higher vibrational energy level, rotational quantum number is 0. In such case, what will get? Delta J minus 1. So whatever the spectral lines we are getting, if delta J is equal to plus 1, such spectral lines are called as R branch lines. Those are called as R branch lines. So R branch lines are observed at omega bar naught plus 2b plus 4b plus 6b like this. If delta J is equal to minus 1, the corresponding spectral lines are called as P branch lines. The corresponding lines are called as P branch lines. And in general, if you see delta J value minus 2, minus 1, 0, plus 1, plus 2. Okay. O, P, Q, R, S. So delta J is equal to minus 1, such lines are called what? P branch lines. Delta J is equal to plus 1, such lines are called R branch lines. Plus 2, S branch, minus 2, 0 branch lines. Anyhow, here O branch lines, S branch lines, and the Q branch lines are not possible. What is delta J value into plus or minus 1? So P branch lines we will get and R branch lines we will get. At omega bar naught, can we get any signal, or at omega bar naught we cannot get any signal? Omega bar naught we cannot get any signal. Omega bar naught is considered as band origin. Omega bar naught is considered as band origin or band center. That is considered as band origin or band center. So here I am writing and this is omega bar naught and that is band origin or band center. We will get omega bar naught minus 2b. At 2b distance we will get a signal. Next omega bar naught minus 4b. At 4b distance means the gap between these two is what? 2b again. Next 6b. So these are called what? P branch lines. These are called what? P branch lines. R branch lines are observed at 2b distance from band center omega bar naught. So at 2b, next one at 4b, next one at 6b. Omega bar naught plus 2b, omega bar naught plus 4b plus 6b. Here omega bar naught minus 2b, omega bar naught minus 4b, omega bar naught minus 6b. Again the gap between this also what? 2b, 2b, 2b. So the gap between any two successive spectral lines is 2b centimeter inverse, but at the center the gap is 2b plus 2b, 4b. Since at omega bar naught we cannot get any signal, at omega bar naught we cannot get any signal, so that means at the center the gap is 4b centimeter inverse. So this is about the rotational vibrational spectra of rigid diatomic molecule. Rigid diatomic rotating vibrator we consider. Rigid diatomic rotating vibrator we consider. Like this we will get various signals. Okay, you remember selection rules, and selection rules are nothing but combination of rotational spectra and vibrational spectra, that is delta J is equal to plus or minus 1, delta V is equal to plus or minus 1, plus or minus 2, plus or minus 3 and so on. In that we consider only one specific case, delta J plus or minus 1, delta V plus 1. In that also we consider V is equal to 0 to 1 since ground state is highly populated. So then these are the various signals we will get. Delta J minus 1 P branch lines, delta J plus 1 R branch lines. The distance between any two successive spectral lines is 2b, but at the center the gap we will get 4b. Okay, so next one, vibrational modes of polyatomic molecules. Vibrational modes of polyatomic molecules. Vibrational modes of polyatomic molecules. Okay, I am taking a polyatomic molecule containing n atoms. Polyatomic molecule containing n atoms. If it is linear molecule, how many vibrational motions are possible? The number of vibrational motions are 3n minus 5. Okay, for linear molecule, the number of vibration motions possible are 3n minus 5. Out of 3n minus 5, n minus 1 are stretching vibrations. Stretching vibrations. Again, in stretching vibrations, we have symmetric stretching, anti-symmetric stretching. Next one, the remaining are bending vibrations. That means here 2n minus 5, 2n minus 4 are said to be what? Bending vibrations. Stretching vibrations means bond length changes during vibration. Bending vibration means bond angle changes during vibration. Okay, so we are taking a linear molecule, okay, containing n atoms. The number of vibration motions possible are 3n minus 1. Out of 3n minus 5, n minus 1 are stretching vibrations. 2n minus 4 are bending vibrations. If you see example, I am taking linear molecule CO2. How many atoms are there? The number of atoms are 3. So the number of vibrational motions 3n minus 5, 9 minus 5, that is 4. Out of 4, how many are stretching vibrations? 3 minus 1, that is 2 are stretching vibrations and 2 are bending vibrations. 2 are stretching vibrations, 2 are bending vibrations. Stretching vibrations, again we have symmetric stretching vibrations, anti-symmetric stretching vibrations. Symmetric stretching vibrations, anti-symmetric stretching vibrations. Again, bending vibrations are of two types: in plane bending, out of plane bending. In plane bending, out of plane bending. Anyhow, these two are degenerate vibrations. Both occur at same frequency. Both occur at same frequency. In plane bending, out of plane bending. Okay, so we consider a linear molecule CO2 containing 3 atoms. Okay, the number of vibrational motions 3 into 3, 9 minus 5, 4. Out of 4, n minus 1, that means 3 minus 1, 2 are stretching, 2 are bending vibrations. Again, in stretching vibrations, one is symmetric, another one is anti-symmetric. In bending vibrations, one is in plane bending, another one is out of plane bending. Okay. Already I explained in the morning session. If both undergoing extension or compression by same extent, if both undergo extension or compression by same extent, that is called as symmetric stretching vibration. One is undergoing compression, another one is undergoing extension. So that is said to be what? Anti-symmetric stretching vibrations. This is symmetric stretching vibration. This is called anti-symmetric stretching vibrations. Symmetric stretching vibration is whether IR active or inactive. IR inactive since negative dipole moment is 0. Okay, change in dipole moment during vibration is 0. Anti-symmetric stretching vibrations. In plane bending under, out of plane bending under. In plane bending. So on this blackboard itself, they are undergoing bending under. These two bonds undergoing bending like this. Okay, here we have like this CO2. They are undergoing bending like this. Okay, like this bending. Okay, so that is called in plane bending under. Out of plane bending under. Okay, above the plane under. Above the plane. Plus indicates above the plane, minus indicates below the plane. Like this under. So on the blackboard itself, previously undergoing bending vibrations. Now above the plane, they are undergoing the vibrations. These two vibrational frequencies are same. All these three are what? IR active, but this is IR inactive, symmetric stretching vibration. And again, these two are said to be parallel vibrations. These two are called as parallel vibrations. Parallel vibrations, and these are called perpendicular vibrations. If oscillating dipole is along the bond axis or along the molecular axis, oscillating dipole is along the bond axis or along the molecular axis, those are called parallel vibrations only. Here dipole is oscillating, your negative sign, here it carries carbon, carries partial positive charge, that is oscillating along the bond axis only. So that's why these two are called parallel vibrations. But here this is CO2, okay, the vibrations are occurring like this. Bond axis is in this direction, how they are undergoing vibrations like this. So Oscillating dipole is perpendicular to the bond axis. Oscillating dipole is perpendicular to the bond axis. So these are called perpendicular vibrations. These two are parallel vibrations. These two are perpendicular vibrations. Okay. This is about linear molecule. And now if you take non-linear molecule, for example, I am taking H2O. Now I am taking non-linear molecule containing n atoms. Non-linear molecule containing n atoms. How many vibration motions are possible? 3n minus 6. The number of vibration motions possible are 3n minus 6. 3 translational, 3 rotational, we have to subtract it. Okay, out of 3n minus 6, n minus 1 are what? Again stretching vibrations. The remaining 2n minus 5 are said to be bending vibrations. N minus 1 are stretching vibrations. The remaining are bending vibrations. For example, I am taking H2O. How many atoms are there? 3 atoms. That means the number of vibration motions are 3 into 3, 9 minus 6. That is 3 vibrational motions are possible. Out of 3 vibration motions, n minus 1, 3 minus 1, that is 2. 2 are stretching vibrations, 1 is bending vibration. Okay. Out of 3 vibration motions, 2 are stretching vibrations and 1 is bending vibrations. Out of 2 stretching vibrations, 1 is symmetric stretching vibrations, another one is anti-symmetric stretching vibration. One is symmetric stretching vibration, another one is anti-symmetric stretching vibration. Okay. For H2O, if you see symmetric stretching vibration, it is a non-linear molecule. See, it follows C to V point group, V shape, it has V shape. Okay. Okay. If these two bonds undergoing extension or compression by same extent, and that is called symmetric stretching vibration. Here, only bond length changes and bond angle doesn't change. OH bond length changes during vibration. That is called symmetric stretching. And if both are undergoing vibration by same extent, that is called symmetric stretching. Here, one is undergoing compression, for example, and another one is undergoing extension. One is undergoing compression, another one is undergoing extension. This is said to be what? Anti-symmetric stretching vibration. This is symmetric stretching vibration. This is anti-symmetric stretching vibration. And another one is bending vibration. This bond undergoing bending, bond angle changing. This bond also undergoing bending, bond angle is changing. So that is said to be what? Bending vibration. Okay. So which is parallel and which is perpendicular, we can also decide based on rotation. If you rotate this H2O, we'll get equivalent configuration or not. We can get equivalent configuration. So this is called as parallel vibration. If you rotate this by 180 degrees, we cannot get equivalent configuration. So this is called perpendicular vibration. Now, if you rotate this molecule by 180 degrees, we can get equivalent configuration. So that is also called parallel vibration. In the case of CO2 also, we can follow like that. Okay. In case of CO2, for example, C, double bond O have. If you consider bending vibration, if you do the rotation, okay, along bond axis, we have to rotate along principal axis. We have to rotate along principal axis. If you rotate along principal axis, what will get like this? Will get. If you consider bending vibration, if you rotate along principal axis, we'll get like this. That means we cannot get equivalent configuration. So bending vibration is said to be what? Perpendicular vibration. Perpendicular vibration. Here, this is the principal axis we have for H2 bond. With respect to the principal axis, we have to rotate it. So same, we will get parallel vibration. Here also we will get same parallel vibration. But here we cannot get same. Here we may get like this. So that is called as perpendicular vibration. So we consider linear molecule, number of vibration motions possible, 3n minus 5. Out of 3n minus 5, n minus 1 are stretching, remaining bending. For non-linear molecule, 3n minus 6, again n minus 1 are stretching, remaining are bending vibrations. Generally, if you see the vibrational frequency for stretching vibration, is more compared to bending vibration. Okay, generally vibrational frequency for stretching vibration is more compared to bending vibration, and generally vibrational frequency for anti-symmetric stretching vibration is more compared to symmetric stretching vibration. General observation. Okay, stretching vibration, it is more energy is required to stretch the bond and compared to bend. To bend a bond, less energy is required compared to stretching. Okay, less energy is required to bend a bond. So generally the vibrational frequency for stretching vibration is more compared to bending vibration, and the vibrational frequency for anti-symmetric stretching vibration is more compared to symmetric stretching vibration. Okay. Here, for example, if you take linear polyatomic molecule, what are the selection rules? Linear polyatomic molecule. Selection rules, if you see, different for parallel vibration and perpendicular vibrations. CO2, if you consider, that is a linear polyatomic molecule, it contains 3 atoms, more than 2 atoms are there. So far we considered diatomic molecules. Now here we are taking polyatomic molecule CO2 containing 3 atoms. Okay, selection rules are different for parallel vibrations and perpendicular vibrations. We discussed for CO2 two stretching vibrations are there present, both are parallel vibrations. 2 bending vibrations are there, both are perpendicular vibrations. Selection rules are delta J is equal to plus or minus 1, delta V is equal to plus or minus 1, plus or minus 2, and so on if you consider enharmonic motion. If you consider harmonic motion, plus or minus 1 only. Okay, so that means plus 1 means we get to which lines? P branch lines. Minus 1 means we will get R branch lines. Now if you consider perpendicular vibration, for example CO2 bending vibrations, the selection rules are delta J is equal to 0 plus or minus 1, delta V is equal to plus or minus 1, plus or minus 2, and so on. Same enharmonic motion. So here, in addition to P branch, R branch, we also get what? Q branch lines, and delta J is equal to 0 means what? Q branch lines. So for parallel vibrations, Q branch lines are absented. Sometimes they are giving signals. Okay, P branch lines are obtained, R branch lines are obtained, like that they are giving the data. If Q branch line is absented, that indicates it corresponds to linear molecule. If there is no Q branch line, okay, if there is no Q branch line, then it indicates that it corresponds to what? Linear molecule. Since for other polyatomic molecules are not linear, symmetric polyatomic molecules are asymmetric polyatomic molecules are spherical top molecules. For them we will get delta J 0 also. For parallel vibrations also we will get 0. For parallel vibrations also we will get 0. So for other molecules, Q branch lines present for parallel vibrations and perpendicular vibrations. But for linear molecules, if you consider the parallel vibrations, Q branch lines are absent. That indicates that if Q branch lines are absent, then such molecule corresponds to what? Linear molecule. Right? These are some points you may remember from vibrational spectroscopy. Okay. One is simple harmonic motion. E is equal to V plus 1 by 2 into H nu or nu bar. Equispaced energy levels will get only one spectral line, that is at nu bar. Next, nu bar expression 1 by 2 pi square root of K by mu. As force constant, as strength of the bond or bond order increases, nu bar increases. As reduced mass increases, heavier isotopes increases, vibrational frequency, vibrational frequency decreases. Polarity of the bond increases, vibrational frequency increases. Okay. Next, morning we compared. What about nu bar values for dBr and HBr? Nu bar value for dBr is 1 by root 2 times 2 nu bar for HBr. Okay. So next one, enharmonic nature. Enharmonic nature, you have to remember Morse expression. For harmonic motion, what is the expression for potential energy? 1 by 2 kx square. parabolic type of graph we will get. According to Morse curve, we will get dissociation, and up to certain extent only stretchings are possible, vibrations are possible. Whenever the energy of vibration reaches dissociation energy, the molecule undergoes dissociation. That is called enharmonic motion. For that, what is the expression for Morse curve? That you may remember. Next, what is the expression for energy for enharmonic nature? Vibrational energy level. Selection rules in every case is important. Simple harmonic motion plus or minus 1 only, but here plus or minus 1, plus or minus 2, plus or minus 3, and so on. 0 to 1 is called fundamental transition, 0 to 2 first overtone, 0 to 3 second overtone, 1 to 2 hot band. Okay, fundamental transition is observed at what? Omega bar E into 1 minus 2 xc. First overtone 2 omega bar E 1 minus 3 xc. Second overtone 3 omega bar E 1 minus 4 xc. Hot band is observed at omega bar E into 1 minus 4 xc. This you may remember. Okay. Xc is called enharmonistic constant, its value is 0.01. Next one, vibrational rotational spectrum we discussed, rotational vibrational spectrum, rigid diatomic vibrating rotator we discussed. The selection rules are delta J plus or minus 1, delta V plus or minus 1, plus or minus 2, and so on. Enharmonic motion we considered, rigid rotation and enharmonic motion we considered. Okay, the signals are observed at omega bar plus 2 Vm, where m values are plus or minus 1, plus or minus 2, and so on. If delta J positive, m values positive will get, delta J negative, m values will get negative. Delta J plus 1, R branch lines will get, delta J minus 1, P branch lines will get. So omega bar minus 2B, minus 4B, minus 6B, like that we will get P branch lines. Omega bar naught plus 2B plus 4B plus 6B, like that R branch lines we will get. At omega bar naught we cannot get any spectral line. Okay. And finally, for linear molecule 3n minus 5, non-linear molecule 3n minus 6. In both the cases, n minus 1 are stretching vibrations, remaining are bending vibrations. If oscillating dipole is along the bond axis, that is called parallel vibration. Perpendicular to bond axis, that is called perpendicular vibration. Okay. That also we can verify by taking principal axis, and with respect to principal axis, we have to rotate the molecule. If we get same configuration, it is parallel vibration. If you are getting different configuration, that is perpendicular vibration. In CO2, stretching vibrations are parallel vibrations, bending vibrations are perpendicular vibrations. In H2O, we observed bending vibration parallel, symmetric stretching also parallel, but antisymmetric stretching vibration is perpendicular vibration. And finally, we discussed linear polyatomic molecules. Linear polyatomic molecules, the selection rules are different from parallel vibrations and perpendicular vibrations. For perpendicular vibration, we will get P, Q, R branch lines, but for parallel vibrations, we will get only P and R branch lines. That means if Q branch lines are absent, then such molecule is said to be what? Linear molecule. Right? This is about vibrational spectroscopy. Next, we will discuss Raman spectroscopy, and in the next class, we will discuss Raman spectroscopy. Okay? Thank you.